Welcome back, and in this video we first talk about some fundamental concepts. These concepts are not only important for neural networks, but they are definitely important for neural networks and for other machine learning techniques. And I would say most of them are, or some of them are important to do before we do anything, so before thinking about the concrete architecture of a model or before training a model, and some other stuff is also related to what to do during training. Okay, but especially if you really use the hands-on approach and directly work with real data, you will definitely benefit to know and also to conduct the principles that we're discussing here. I'm also trying to build an example or like a bigger example tutorial in the future where we will take a look at most of these concepts in reality with a real data set. Okay, but for now, let's quickly discuss them in theory. And this is really something that you should always be aware of and that you can benefit from if you are aware of these concepts. Okay. So the only thing that we will not discuss into too much detail here is the gradient-based optimization that we're usually using, because we already discussed its idea in a previous video. Then, of course, we will talk about data pre-processing. So as the name suggests, this is something that we need to do before we will estimate the model. And then we will discuss things that are supposed to be done with respect to training a model, but making sure that it generalizes, or at least to evaluate if it generalizes. That means if it also works well for new and unseen data, and other aspects like over and other things, for an example, or regularization and stuff like that is related to this, and we'll also discuss this. Okay, so first, but only as I said, just a few more notes with respect to gradient-based optimization. So typically our models, they will be depend on a set of parameters, so they need to be calibrated, and we use training data to calibrate the model. This means in our case that we will use a loss function. The loss function for all the observation gives us feedback if the predictions made by our model work as they should. So if they are, for instance, close to target realizations, and we try to achieve this on average for all data in the training data set. And to calibrate the parameters, we minimize the loss function by setting the parameters. So we have a minimization problem, and this is usually solved numerically or approximately numerically by the gradient based method. And it simply is that we have, let's just quickly go there, we have typically a loss function and usually a set of parameters, but assume we only have one parameter. Then we start at some random value, and then the gradient of the loss function is the information that we need to find out if we further should increase or reduce this value in order to reduce the value of the loss function. And usually we will have a training data set, so a whole batch of observations. So the whole batch, or is the training, are all observations in the training data. And the only thing we left out in the video before is that especially if we have big data sets, then we will not use all observations typically. We will use only a mini batch of it. That is, so all data would be the batch. Okay. Now, if all data is a lot, then it's a lot to compute for our model, and it may take too long to train the model, which means to calibrate the parameters. We also can do as the optimization is an iterative procedure, which means we have many different steps. For many times, we adjust the parameter, then determine the loss value, determine the gradient of the loss value, process this information and generate new parameter updates. All this is done within multiple steps. So if the data is too much, the most extreme approach to reduce the computational intensity is to use only the information of a single observation for each step. Okay, so the way we learned it in the previous video is that we would use all observations, so all gradient information with respect to all observations and the corresponding value of the loss function for all observations. The most extreme alternative is, in each step, only use a single observation, use its gradient information in order to make the parameter update. And now, as always, something in between usually works best. So what is typically done, especially when we use Keras, for instance, is that we randomly draw a so-called mini batch. So that means we do not use all observations, we do not use a single observation, we use a subset of all observations, which is randomly drawn for each iteration, and use the subset in order to determine the loss and the gradient information, and to make the parameter update for this single step. Now in the next step, we again randomly draw a new subset, so may have some of the observations from the previous step within, but also some new ones. And this is how we proceed when it comes to stochastic gradient descent that we typically apply. And also something which we could way more into detail is the learning rate. So the way how we change the parameters based on the gradient information during training the model is, in our example in the beginning, it was a constant value, but there are more sophisticated approaches which also make sure that the learning rate is dynamically adjusted during the iteration steps. And the basic idea here is, without going into detail, that of course in the beginning we may be far away from the best parameter estimates, so our learning rate can be higher, which will generate larger parameter updates with respect to changes in their absolute value. But then after some iteration, we may already approaching like the best parameter values, and then we should make sure that the learning rate is not too high, because otherwise we will overshoot and then end up in an area which is far away than we have been before. So there is usually some dynamic adjustment of the learning rate, and also we have different approaches, different algorithms that can be used, especially for instance later if we use Keras to define the model and compile the model, then we will give an algorithm that deals how to best adjust the learning rate during training. Okay, but this is all you need to know when it comes to the estimation, and it would be worth to dig deeper here, but due to the time limitations that we have, we will skip this, and I will leave this up to you if you want to take a more detailed and look into it, and we will go on and move on to one of the next fundamental concepts I think is important when we work with real data. And so first we get a training data set. In the beginning usually these will be CSV files, so not that big of a data set. Sometimes later maybe we will get simple bases like an SQLite database or something like this, which is already capable of having multiple gigabytes of data, so big data sets also. But we get the data, and it randomly it seldomly is the case that we directly can start working with the data, because we need to prepare the data. There are some things that we need to do, and that is what we want to take a look also in the next videos when I present an example with real data to you. But obviously sometimes it is necessary to clean the data, which means that we need to think about what should we do with data. Some single observations may be missing, for instance. What should we do with them? Should we delete them from the data set? Can we replace the missing values with some representative values, stuff like that? So that is also why we want to, in the first step, always get some information of our data set. How many variables are in there? Are there any missing values? Then we can maybe take a look at visualizations of the data in order to find out already if there are outliers, if there's something strange going on. Okay, and Then also we often have categorical data, which is then often or usually given to us in textual form. So I don't know, for instance, could be the information if for the single feature it's a male or a female person. Our model will not be able to calculate with the information male, so we need to encode it. For instance, say 1 corresponds to female, 0 corresponds to male, and stuff like that. And also feature scaling is an important thing we will discuss in a minute. Okay, so if we start with a data set, what I will always do is, there are some nice information. Usually we will work with pandas. Pandas is a package that is built for handling data sets in Python, and it comes along with many nice informative methods and functions. So for instance, pandas has a function which is the info function, and the info function already tells you how many variables are there, how many observations do we have, and are there any missing values. And missing values is kind of an important aspect, because in some cases for instance, for a specific variable, there may be only a few missing values, so only for a few observations this value is not available. Usually in your data set this will be an A or so not available, or an NaN. So I guess it's not available number or whatever. And we need to think about what to do with this. Usually our models are structured in a way, or are built in a way, that they only are able to process the information by all feature variables. So for instance, if we have many feature variables, but for a given observation only a single observation for a feature is missing, we either replace the missing value with a representative value that makes sense, or we need to delete the complete row. So we need to completely delete this observation. Only these two possibilities do exist if we observe a missing value for a single realization of a single feature variable for a single observation. Okay, so kind of depends, I would say. So if you have a variable that has many missing values, then sometimes I would say it makes sense to delete the variable at all, because if there are so many missing values, it might be the true reason for it might be that it is really hard to observe it, or this information is, I don't know, maybe really hard to get. So we just should delete this, because it will make also trouble in the future to get this information. But if there are only a few missing values, I would say it's always worth try to save as many observations as we can for our data set, because the more data the better usually, because the more data the better we can train our models. And the process of replacing missing values with representative values that hopefully make sense is also called data imputation. And usually there are two ways to go, and most popular or most common ways I would say is the univariate method, but also multivariate and more sophisticated methods exist. So sounds sophisticated, but especially when it comes to univariate data imputation, what you basically do is you take a look, for instance, at all the observable realizations for a single feature variable. And then, for instance, if it's a numerical value, then you take just the average of all these values as a representative for observations where the value information is not given for this feature variable. Okay, so it's like the arithmetic mean or the median in case of numerical feature variables, or if we have a categorical feature variable, then we would take a look what is the most common category of this feature variable in the data set, and then we will use this as a representative for the missing observations, for the missing realizations for this specific feature variable. Multivariate data imputation is that you do not first take a look at like the target variable, but among the training data and the feature variables, you build models for the feature variable with the missing values, and you use the observations for which you have the realizations of this feature variable in order to train a model to predict the values for the missing places. Yeah. All this, we will not discuss it in detail, is very well described on the sklearn homepage or documentation. Let me just zoom in here. Just you can Google it, or you just take a look at the address here above. But here is a well-written documentation about imputation of missing values, about univariate and multivariate, and also with example code how to do it. We will, as you can see, we will take a look more into for different things, aspects here, because really sklearn documentation, I think, is quite good, and especially for these more kind of pragmatic things. Yeah, it's always enough to check out this here and see how it works. And I think this is not really sophisticated science, so I think it's quite easy to understand what's been done here, and also how it's been done is better understandable, especially if you see these simplified examples for yourself. Okay, so imputation is something you should need to be aware of. You should, in the beginning, you should need to be aware of your data, how it looks like, and is your data plagued by missing values, and if so, can you do something about it? Because, as I said, our aim is always to get as many data points, observations as we can, because this helps us usually to train our models. Obviously, there's a trade-off, because the more missing values we have, and the more the model is messed up by replacing actual observations that we do not know with representative values, which typically will deviate from the observations that would have been in reality if we could observe this realization. Okay. Now, the next step, at least I'm always doing, is then to check what kind of variables do I have. Are these already always numerical variables, or do I also have category variables in the data set? Usually in pandas you will have a good indication about this. Of course, category variables can already be encoded in a numerical way in your data set, but usually this is done by using integer values. So you can check out the feature variables that are given by integer values. And this is usually an indication that this is already some form of categorization, or sometimes you may have just textual information for a variable, so like male, female, bi, cell, whatever. And this obviously, the text needs to be encoded into numbers such that our models can work and deal with it, because our models are based on math and matrix operations. And this can only be done, or at least only defined, for numbers. And usually I would say what is done is either one-hot encoding or also a label encoding. So yeah, one-hot encoding is the amount of categories we have for a specific feature variable, is also the dimensionality that we need to represent this variable in one-hot encoding. Which means if we have, for instance, 3 categories, then we need a 3-dimensional vector in order to indicate whether this is a center, suburb, or countryside apartment. So if it's a center apartment, then we have a vector which is 1, 0, 0. If it's suburb, it's 0, 1, 0, and countryside is 0, 0, 1. So it's always 0 except for the category that it actually is. That's where the name one-hot encoding comes from. Okay, so basically what we have for each category, we have a binary variable which is equal 0 or 1, and it is only 1 if it really is this category for the specific observation. Of course, there's also the possibility to label encode it simply. So we have like in ordering, like 1, 2, 3, 4, 5. But this obviously rather makes only sense if the category variable really has is of ordinal nature. So if it's really 5 is really higher than 1, or I don't know, if there's some form of ordering, so 1 may be better than 5, for instance. Only if this is like the true nature behind it, then you should not one-hot encode it possibly, but you know, like use a label encoding or something. So an ordinal encoding, sorry. Also, this is very well implemented and documented in the sklearn preprocessing library. As you can see here, if you Google this, you will definitely find this site. And then if you, for instance, go here on the one-hot encoding, you can read about what's done here and how it's done, and you can already see the method, how it's defined in Python. And then, as always, you find here some smaller examples, which are, yeah, I think always very valuable when it comes to a better understanding here. And also the ordinal encoding is obviously described in a very similar way. And yeah, so I think that's all that needs to be said about it, but also obviously a very important aspect, how to include your category variables in the model, such that the information provided by the category variable you know, is processed in the appropriate way. Okay, now another very important aspect, and this is usually very important when we have some form of classification problem, is that the categories, and usually of the target variable, is usually not balanced. That means the frequencies of certain categories, or that means the frequencies of each category usually are not the same or not similar. So because many times, for instance, we have stuff like a fraud detection problem, and fraud only happens in only a few cases. So assume we have a fraud detection problem, and fraud is, you know, it's encoded 1 if a person commits fraud and 0 otherwise. And then, I don't know, we have 10 out of 10,000 fraud committing people. Then our data set is very unbalanced with respect to the target variable, because the frequency is only 10 out of 10,000, and for the you know, category of interest, and the remaining, so the counterfraction is the one for the category which isn't really of our interest. So that is what's called a really like an unbalanced data set. And also, for instance, default prediction. Yeah, usually people do not default, but obviously banks are very interested in predicting the people who default, and this is typically a minority in the data sets we are going together, because most of the people will not default. But the problem is, if we use the data set in this unbalanced way, then the most of the observations are related to the target, that category we're not interested in. But obviously then our model is trained with a great emphasis on the category that we are not interested in. So we can do two things here. We can downsample or undersample the data. That means we simply delete a lot of the observations we are not interested in, so the 0 categories. Obviously, this is usually a bad idea, because we need as much data as we can in order to you know, estimate stable and generalizing models. Or we can oversample. So I would say oversampling usually is the things you should seriously consider. Only in a few cases where really you have a tremendous amount of data, downsampling would also be a reasonable approach. But oversampling means that we artificially create observations for the category of interest, or for the category which is underrepresented in your data set. And also for this, we have a very, very good documentation, also again from the sklearn package. If you just search for it here, like the imbalanced learn, so it's basically, it's another package, sorry, but it's related to it. And here we really have a very nice introduction, and with good examples, and also with different methods, how like what kind of methods exist in order to oversample the data or to generate new artificial observations. We will take a look at just one here, just to get an idea how this can be done, because it's kind of sounds quite fancy and sophisticated to say that we artificially generate non-existing observations. So yeah, this is the formula one of the algorithms called SMOTI uses, but I would say let's just directly dig here into a concrete example. So assume the orange dots here represent to the category of interest, which could be encoded with ones in our data set, and the blue dots here are the other category, which is encoded with zeros. So, and these are here the two feature variables that we have. So here x1 and x2 could be two feature variables providing information about the target variable, which is either 1 or 0. And obviously for the orange, so for the category of interest, it typically occurs here in this area, so with lower values of x1 and also lower values of x2. And so each observation here is, in terms of their feature variables, can be represented by a vector, here a two-dimensional vector. So for instance, these would be the two data points here. And what SMOTI does is, to randomly draw two data points, so two vectors, so to say, with respect to the feature representation, and then draws a line between those two, always of course of the category of interest, and then samples another number that randomly puts a dot here, so an observation on this line, and this is then our new artificially generated value. Okay, so now we can take a look at the formula. So we start with from a point. Could be, for instance, this point here, and then with a certain number which is between 0 and 1. The more close it is to 0, the more close it will be to the original point, and the more close it is to 1, the more close it will be to the other point that we also randomly draw, which is here. So we start at the original point and then move with a certain fractional number on the line that is then calculated here in order to generate a new observation. And of course, this observation are then feature variable realizations that we did not observe. So assume we observed this value here and this value here, but obviously we did not observe a realization with feature variables that correspond to this point. But obviously this point seems to be somewhere close to other points which are related to the category of interest. And that is why we use this point and treat it as it would be also a feature representation for the category of interest. And that's it, basically. So this is how it works for, how it works for the SMOTI algorithm. If we have real valued features, just a quick note, so we always have a starting point, then we sample a similar point, so a point which is close to this one. The closeness is measured by the Euclidean distance usually here, or in a higher dimension, for instance, by cosine similarity. And then we have 2 points and we draw a line between 2 points. And somewhere randomly on this line, which is given by lambda here, we will find a new point. This also can be done if we have additionally some categorical features in this vector here, then the SMOTI NC algorithm. But I think, yeah, like this is the most important part here. This is to understand how it works. Okay, so this is how we can artificially, for instance, generate new data. And there are also other algorithms available, for instance, the ADASYN algorithm. And this is where I would recommend you just to, grasp the idea of these algorithms here. And as I said, we are always somewhere in a trade-off between really focusing and understanding all the details of the methods we are applying, which is obviously favorable, but there are so many methods nowadays that in the first step I would always recommend you to first try to get an idea and you have to at least have a rough idea how it works. Never do something where you do not have any idea how it works, but in the first step I would always recommend you read the documentation, see that you really get an idea how it works, And if it works, then for your problem, after that, really make sure that you understand the details. Okay, so this is how I would recommend it, and this is how we are going through this course here. So that is why we are now not focusing into more detail here. This is something, for instance, that you can do in your project assignment for the course, or maybe later when you're really using some of the methods. I would say all the methods you're really using, then make sure you understand them in detail, and for the remaining methods, just to make sure that you are aware that there are other methods, and that you, in the best case, also have the rough idea of them in your mind. Okay. Good. So this is what I would say is the most reasonable way of oversampling. Obviously, the other alternatives do exist, for instance, as using just different weights of the observations. So we could upscale the weights of for the observations of the category of interest in our data set, but this is simply as you would copy the observations of the category of interest that you already have. And I think the oversampling approach, if the artificial generation of unseen new data kind of works, then it's better suited to train models for generalization. Okay, then not mandatory, but I would say mandatory for neural networks is to make sure that all your feature variables, and I think it also makes sense to make sure that the target variable, they are on a very comparable scale, which means that they are on a very similar numerical range. So that is achieved by scaling the data. For neural networks, it's kind of mandatory to do this because it potentially will lead to big problems from a numerical perspective if you do not do this, and this may also hinder your model from learning and from being fitted to the data, which means that it can also generate quite big problems to find good parameter calibration, parameter estimates in order to generate a network that makes good predictions. Okay, so always make sure to think about the scaling of the data before you do anything with it. For other models, it's not kind of that important sometimes, but I would say it usually can help. So it's you cannot do, in my understanding, as far as I'm aware of it, you cannot do nothing bad by scaling the data before fitting a model, no matter which model you're using. So there are also very different types of scaling available. I would say the most common ones which are typically used is either min-max scaling or standardization. So let's first discuss this. Min-max scaling, and also this usually is done for the numerical variables only, it brings for a single feature variable, it brings its realization to the range between 0 and 1. How is this done? So this is always, think about it per feature variable or for the target variable. We will find per feature variable its minimum and its maximum value, and then we each realization we subtract the maximum value, and then we divide it by the overall range between the maximum and the minimum, and by this way each observation or each realization for the feature variable is between 0 and 1. Scaling standardization means for each feature variable we will derive the arithmetic mean and typically the standard deviation, and use this form of standardization. So that means for the training data, which we use to calculate the mean and the standard deviation, if we really apply this kind of standardization to all the realizations of the feature variable, then it will have the standardized form will have a arithmetic mean of 0 and an empirical standard deviation of 1. Okay, so that is what standardization is about. There are many other things, and especially in recent applications recent experience I made on my own, this can be sometimes problematic, especially if we have outliers in our dataset, outliers with respect to the feature variables. So I would also recommend you here to take a look at the pre-processing data documentation in the sklearn package. And here it first guides you through the common things that we discussed for a second ago, but it also will show you other approaches. For instance, if you have sparse data, which is for the moment not so important, but also if you have outliers in your data. And there are robust scalars, but also there are quantile transformations, and for instance, the quantile transformer, and so on and so on. As I said before, nothing really that I want to go too much into detail here, but important to know that these things do exist. And I would say, from my recent experiences, always worth to check out different standardization or scaling methods when you're really estimating a model because it can sometimes, usually doesn't, but sometimes it can have a tremendous effect on your model performance. But the important part for you is here, have in mind, typically you need to scale your data. Okay, you need in some form to normalize it or bring it to comparative numerical ranges. Okay, last but not least, so now assume you have the data. Assume you have cleaned it, assume you have encoded it, you have scaled it, whatever. Typically before scaling already we split the data. So we have an overall amount of data, but we split the data. Why do we do that? Because, as I said, most important for us is that our model generalizes. So that means we do not only want our model to work for the data that we observe, we also want to work and generate good predictions for new and unseen data. I think obviously this is important, okay, because only if it works for all kinds of data, then we really have a model that we can use to derive about the general, information about the general relationships between the variables in our model. So if we would do this, then it would be enough to have a training data and a test data set. So usually we have a split here, like 60 or 70% of the data that we have are used for training the data. The remaining data is used for testing the data. But in some or in most of the cases, we have also hyperparameters. So that are parameters that are not directly trained and adjusted by the optimization during training. So for instance, in our neural network, the choice of the activation function is a hyperparameter. The number of layers is a hyperparameter. The number of neurons in a layer is a hyperparameter. The learning rate used for gradient descent is a hyperparameter. And of course, hyperparameters are something which is set by us, but it can have a big impact on the overall performance of the model. That is why we usually have three splits or two splits. So we have three subsets of the overall data. We have a training data, a validation data, and a testing data set. The training data set is used to calibrate the parameters of the model. So here we have the optimization routine and generate the parameter estimates. Then, and we'll do this for a certain hyperparameter setting. Then we will check out the performance with respect to the validation set. And here we can do this for different hyperparameter settings. So that means our training data is fitted, so the parameters are impacted by the training data, but the validation data already is unseen data with respect for these parameter estimates. And here we can evaluate which hyperparameters may seem to generate better out of sample results than maybe other hyperparameter settings. But then, for instance, we have, we compare three different hyperparameter settings, and then we choose the setting with the best results for the validation data. And now we use this model, so with this hyperparameter setting and the corresponding parameters that are used or that are learned for the training data, then finally we'll also use this to evaluate again the overall model with respect to the test data. Okay, so that is why we it makes sense to have three subsets of the overall data we have. Okay, then of course doesn't end here. We have something also to keep in mind when we make this split of the data into three subsets. Usually this is either drawn by randomness, so we randomly draw some observations for the training data, some observation for the validation and the test data. let's for the moment say we can do it like this. Can be critical for financial data due to temporal dependencies that we usually observe, but for the moment, let's say it's okay to do this. Then obviously all the procedure I described so far, like making the validation, checking hyperparameter settings, evaluating the test data, is also driven by this randomness. So it depends on which data points we randomly have drawn for training, for validation, and for testing. In order to make sure that our performance of the model is not really driven by this randomness, because there may be some cases where by randomness we really have better results than we should have, and this is just driven by the way we randomly have drawn the data and split it into training, validation, testing data. So really to make sure that there is no impact on our overall model results by the way we split the data, it is usually best to repeat the procedure of finding hyperparameters, calibrating the model parameters, and evaluating the model, not only once, but do this many times. And this is called cross-validation. And a very popular approach is k-fold cross-validation. So that means we would split a data into equal-sized folds. And then, for instance, we could use, let's say we have 5 folds. We use 3 folds for training, 1 fold for validation, and 1 for testing, for instance. Okay. And we do this many times, and always we'll be interested in the results of validation and testing data. And we'll see this later in another video how this works, okay? But this is also something that you need to keep in mind, and that you also need to do when you want to optimize your hyperparameters. As I said, be aware that the simple random split of the overall data into the subsets is really something that can be threatening or can cause problems for financial data, because financial data is often driven by temporal dependence. That means we have some correlation over time in many of the variables, and it kind of messes up the general relationships if we simply break these temporal dependencies by randomly splitting the data. It only doesn't make any problems, I would say, or this is my understanding, if we have also feature variables in the data set that are able to represent like the systematic evaluation or the systematic dependence over time in financial markets. Okay, but this is going to lead way too far for the moment. And just to be aware of this, just saying this that you heard of this for a single second, for the moment, just do not think about it maybe too much. Otherwise, it may be complicated or more complicated than it is, and hinder you from learning the basic principles here. When it comes to hyperparameter optimization, also for this one, I'm quite sorry, but this is how the word is nowadays. There are also very sophisticated and really efficient packages that help you to generate good hyperparameter settings. So for instance, here we have the Sherpa package. Name, kind of, I don't know, funny and sad at the same time, I would say. But this is, I just want to tell you about that this exists. And as always, if you want to apply it later and want to play around with it, make sure you really understand the basic idea here, read the documentation. But hyperparameter optimization we do this manually very easily in an example, and that's okay for the beginning. But if you want to do this professionally and generate well-performing models, then you should give this a go and try it out, because it may further improve your models. Okay. Good. So sorry for this very long-lasting video, but I would say we do it in one shot, and then we are good to go and continue with our neural networks. Okay, but so I think this is more or less like the last part here, and we will finalize it with something which is related to it. Over and underfitting. Okay, so if you're already kind of tired from the length of this video, click pause, get a coffee, make a short break, and come back, because I think this is a very important aspect, and you should really be able to concentrate and focus now. Okay, Because over and underfitting is very important, especially for neural networks which are capable of grasping or are capable of modeling very complex and nonlinear relationships. In a very abstract way, we see especially when we have a single target variable, we see the world as this here. So our model is responsible for modeling the deterministic part, so the deterministic relationship, a functional relationship between feature variables and a target variable. But in the financial world, especially in the financial world, it is not possible to completely predict always the reality simply by knowing stuff, by getting information, feature variables, because a lot of our reality is also driven by randomness. And so our model is the deterministic part, and here we assume some functional relationship between feature variables and the target variable, but also we have randomness. And the problem is when we have training data, we only see the reality and we do not know what of the reality now is randomness and what is deterministic. With a very advanced model and very complex models, we are able for the training data to completely capture the reality. But now this will lead to overfitting usually, because as the name randomness suggests, part of the reality is randomness, and randomness will be different for new and unseen data. So if we train our model to completely capture the current reality, it will also completely capture the current randomness, which will be different in the future. So our model will fail in the future. Okay, so this is the problem of overfitting. And underfitting, I would say it's quite easy. So if you're not using the right feature variables, if you're not using a function which is complex enough to find out about the real complexity and of the deterministic part here, then your model will perform badly because it really underfits the data. Okay. Best explained, I would say, with this picture here, which I've stolen, I think, somewhere from the sklearn documentation. Okay, so here we have a single feature variable and a target variable and a true function. So the orange curve here is the deterministic part. The randomness is the deviation from the observations, so the samples here, of this true function. Okay, so for instance, for this here above, the randomness is this range here. But for instance, for this point, there is almost no randomness. Okay, so this is how we see, how we picture our modeling world. Now, if we would use a linear regression model and fit it to the data, it may look like the blue line here. And this is what is meant by underfitting, because we do not only have deviations from the true function due to randomness, also these deviations are given here because of the I would say the lack of ability of the model to capture this nonlinear behavior here, so the nonlinear relationship between the feature variable and the target variable. Obviously, an appropriate model would capture the progression of the orange line here, but will not go through all the samples here because it allows for randomness that we will also observe in the future. An overfitting is a real complex model, so it really, like the progression of the blue curve here is quite complex and exhibits very, unsteady progression here, but it almost goes through all the examples here. But this leads to overfitting because it also fits the randomness here, so the deviations between the orange line and the blue dots. And for instance, assume for this dot, it, has a feature variable here, let's say -3 or whatever. So for a new observation, which also have a value of -3 here, the randomness may be different, so it may be here. So now if we would have been here, then obviously the deviation between the blue line and the new point here is way more bigger than we would have if we would have grasped the true deterministic relationship here. Okay, so I hope this helps. to understand the world how I see it, and I think how other people hopefully also see it. And this is where over and underfitting comes from. And over and under, so especially overfitting, can also have different origins, but neural networks are quite prone to overfitting because if we're using many layers, if using many neurons, they really are able also to capture, to create functions which look like the blue line here. Okay. In order to find the best of both worlds, in order to in order not to use too restrictive models, but also not to overfit, we usually use models which would be able to, would be able of this, what you see here with the blue line, but then we hinder them during learning, such that they are forced to do this a little bit more easily, so that to approach the true function as it can be seen here in the middle here. And the way how we hinder them is called regularization and can be done in different ways. And I would say the most common ways is L1 and L2 regularization. That means we add something to the overall loss function, which is the higher, the more complex our model is. Okay, so especially regularization can be imagined quite easily for typical regression problems. So, but also for neural networks, for instance, if we add the, this is like the sum of the squared values of all the parameters that we are using, and this is the sum of the absolute values of all the parameters we're using. Lambda is just our way to say how important we think we should penalize the model, because penalization is done here. Remember, the loss function is something which is supposed to kept minimal, so small numbers are good. And if we add something here that gets bigger the more complex the model is, then obviously this leads to an overall value of this new loss function, which we would consider as bad because it is higher. Okay, so we add something here by telling our model, okay, by it's not telling, it's like introducing a trade-off. Adding something like this here introduces a trade-off to a model. It says, okay, you can use more, which may decrease the original loss value, but overall it should be worth it. So the overall value of the new improvement, and so that's something which is added, which is the higher, the more complex you get, it should be really worth it. Okay, because if we get more complex, then this is going to be higher. And this is higher, and this is maybe lower. Okay, so and this trade-off need to be outbalanced, and this is outbalanced by the regularization. Here we have either we use the sum of the squared values of the parameters, or the sum of the absolute values. Both types of realization kind of work different or have a different impact. Usually, as far as I'm aware of, L1 regularization more leads to models that use less variables. L2 regularization leads to models that use all variables, but in a kind of manipulative way, which hinders them from overfitting. Another thing also, which is, I would say, most easy for neural networks, is the so-called dropout. This is, I would say, very specific to neural networks, but as we are mainly working with neural networks, exactly the right thing for us to do and maybe to learn about. Let me just go here to another document, which I would say visualize it quite perfectly what the dropout is, and exactly what you can see here above. So dropout, usually we have this, this sketch, yeah, right? This is how we picture our neural network for a single observation. And we have the neurons here, and all the neurons are somewhat connected. That's why we call it a fully connected dense layer. When we use dropout, then for each iteration during training, so each time we derive predictions, we get the loss value, we get the gradient information, and adjust the parameter updates, we randomly skip a few of the neurons when we use a dropout. So when we use a dropout of 50%, then for each iteration during training, we sample, I don't know, something which tells us that 50% of all the neurons here are going to be skipped for just the next iteration of the training, and we only train the weights which are not skipped. Okay, so this is that during training we not use all the neurons all the time, and this makes our model bad with respect to being adjusted or calibrated towards the training data. But also by this way we make sure not to overfit to the training data. That's it. I think a very elegant and kind of intuitive and easy approach also to hinder our model from overfitting. And so like regularization can be seen as some kind of manipulation of the model that manipulates it in a bad way during calibration and during training with respect to the training data. Okay, I think that's like the most important part when it comes to the fundamental concepts that are somewhat related to the process of fitting the model. Because the process is we get the data, we need to pre-process it, we need to find an architecture, we need to model it, we need to calibrate the parameters, and we need to make sure that it generalizes. Last but not least, once we have found once we think our model evaluation, or like not evaluation, once we think our model calibration is done, then we are also also want to focus on how well our model performs, and that is why we also need some performance measures. And also there are many different performance measures that can be used and should be selected with respect to the specific task, so regression task, classification task. Find also here some, I think sklearn also has documentation which provides a high amount of performance measures, but here like the most important parts is like the root mean squared error or the mean absolute error of when we have regression type problems. And of course we are always interested in the accuracy if we have some form of categorical prediction problem. And also for the categorical prediction problems, it is often very important to dig deeper than just accuracy. We also want to find out for which categories the model performs good and for which it doesn't. But this is something, as you can see here, I held it very compact, and this is just to remind you that of course performance measures are also needed during the calibration and estimation process, because already here when we want to find out what are good hyperparameter settings and stuff like that, we also need the performance measures. But we will dig deeper here and find more about them with the hands-on approach and working with real examples, because otherwise this also would be a topic that should be related to, I don't know, 20 or 30 or 40 slides, and not only 2 or 3 slides, as you can see here. Okay, so very long video, and sorry for that. I try to keep the videos shorter in the future, but I thought it makes more sense like to have all this what I call fundamental concepts into one video. In between, you also are welcome. You press the pause button, get a coffee or a tea or whatever you like, and come back later. But now we are good to go to really start and getting excited about the more complex and fancy architectures of neural networks, because now you know what a basic neural network is, you know how to train and calibrate it, you know what to be aware of when you work with real data, and now we can continue with recurrent networks, convolutional networks, and take a look at stuff like autoencoders and general advisory networks, which are, I would say, fascinating and very interesting things. So be excited about it, as I am always, and see you in the next video. Bye-bye.